The first example to go over is this one I mentioned at the beginning of last time, calculating the length of the graph of a function. If over here we have a graph y equals f of x between x equals a and x equals b, what we'd like to do is we'd like to turn it into a parameterized curve. In this case, one way to parameterize it is to say that, well, let's just imagine that an object is riding along this curve, moving uniformly in the x direction as time goes on, and its y direction varies. So to make this into a parameterized curve, I say that c of t is equal to t, comma, f of t, because y is equal to f of x. Then its velocity is given by taking the derivatives. 1 is the derivative of t, and f prime of t is the derivative of f of t. And then if we take speed, we take the length of that. That's the square root of 1 squared plus f prime of t squared. And so to calculate the arc length, we integrate from time a to time b this speed of the object. That's where the formula for the length of a parameterized graph comes from. Another example is given by this curve that's moving inside three-dimensional space. It's not related to a graph at all anymore. It's given by cos t sine t, and it kind of spirals up like this. To calculate the arc length of this, c prime of t is equal to the velocity vector. The derivative of cos is minus sine. The derivative of sine is cos, and the derivative of t is 1. And so the speed is equal to the square root of the sum of the squares of those. But here we're going to be taking minus sine squared plus cos squared plus 1 squared, and that's going to be actually equal to the square root of 2. So to calculate the arc length of it between time A and time B, we integrate the speed. This object is basically moving at constant speed, and so even though it moves on a complicated path, it's not that difficult to finally figure out what the total distance it traveled is. It just depends on how long of a time period we look at.